2A, 2B review. So how about we just do more metrics-based questions, like the homework questions? Is that good with all of you? Or because I feel, everyone pretty much knows like what a series is and geometric series and all those tests. So, okay, yeah, let's just do that. So, okay, so let's get started. Sorry, let me get rid of this. Okay, so let's start with the homework question. So this is one of the reasons why I don't like the book. So if you do 13.1 part B, the answer is sort of immediate if you read the lemma 13.3, word for word. So if I go to lemma 13.3, right? Because what does it mean to show, a distance, a metric is complete? It means you assume there's a Cauchy sequence, and then you show it converges, right? So D1, D2, complete, right? So assume, xn, this is a sequence in RK, right? So, sorry, xn sequence. So each xn has like k components. Assume xn is sequence in RK is Cauchy. With, to say it's Cauchy, you need a distance, right? So like with respect to, let's say D1 first, right? It doesn't really matter. So if you just read lemma 13.3, I'm going to use the second sentence. So I'm Cauchy in RK if and only if I'm Cauchy, each component is Cauchy, right? And each component is an R. So it's basically saying I'm Cauchy I'm Cauchy in RK if and only if I'm Cauchy in each component. So so this is so let me just write wrong proof. You sort of see why. So xni is Cauchy sequence in R, right, for all I, by lemma 13.3 second sentence, right? And we know R is complete, right? So each xni converges by definition, right? Complete means every Cauchy sequence converges, right? And then we use the first sentence of lemma 13.3. So we have a sequence converges in R, and that implies that it converges in RK, right? If it converges in R for all I. So converges for all I. So lemma 13.3 first sentence gives xn converges in RK. So you sort of see, like, it's sort of immediate if you just read the lemma word for word. Sadly, this is why I don't like the book. They, here it's, it's only for us. The lemma doesn't state what metric they're using, and it turns out they only prove it for the metric given in example 2. So they only prove it for one specific metric, and it's it's given by this one, right? This d of xy is, sorry, I don't know what's happening. This d of xy is xj minus yj squared. But you can sort of see, if you didn't read that if you just ignore this part, the proof is correct, because this one, it's it doesn't state what metric. So it seems like it's saying it holds for any metric. And the sad part is it's actually true for any metric. So if you learn some harder machinery, it turns out all norms metrics on RK is equivalent. So like they're bounded above and below by constant times and not the other distance function. But that's overkill. So sadly, we can't just use lemma 13.3. So yeah, but I can see why people might have thought that. So okay, so let's go over the actual proof. Yeah. So is everyone clear on why, 13.3 it doesn't work? Okay, no questions. But so 13.3 works for, d of xy is for this distance, right? Xi minus yi. So since it works for this one, the point is relate d1, d2 to d. That's the goal, right? So we know everything works here. So let's relate d1, d2 to d. So just recall d1 is max, I think, xi minus yi, right? And d2 is the sum, I think. Okay, so let's do d1 first. So obviously, let me just sort of show you, like, without loss of generality, like, assume, I mean, the max is one of them, right? So, I mean, if you just reorder the numbers, like, let's assume it's x1 minus y1, yeah? Just for simplicity. I mean, so you see here, I'm certainly bigger than d1 of xy is certainly smaller than d of xy. Why is this? Because let's write out what d of xy is. D of xy is, instead of writing sum, I'm gonna write, the whole thing. So x1 minus y1 squared plus x2 minus y2 squared all the way to xk minus yk squared. And this is to the 1/2, right? And that's certainly bigger than or equal to if I just ignore this, right? If I just ignore it as I'm adding less things, so my thing becomes smaller, right? And this is just x1 minus y1 squared to the 1/2. And this is just x1 minus y1, right? Which is the max, we sort of assume that, that's why I sort of assumed that it's the max, but I mean, just for simplicity. So everyone clear? So, and then this is d1 of xy. So we have a bound, sort of, d1 is sort of bounded by d of xy. Is everyone clear so far? Okay, great. Now, how do we bound above? Well, d of x, let me just write the whole thing out because I think it's easier for everyone to see. So again, if without loss of generality, let's say x1 minus y1 was the biggest one, then this is certainly smaller than if I just replace every term by x1 minus y1, right? And how many terms are there? Well, there's k terms, right? So this thing is k times, what is that? Squared to the 1/2. So this is root k x1 minus y1, which is root k d1 of xy, right? So I have this thing right now. Well, sorry. I need a root k. So hopefully you see why we're doing this, right? It's because lemma 13.3 only proves it for d. So we have to relate all our distances to d. Okay, is everyone clear so far? Any questions? This is just, bounding. So great. Okay, so let xn be Cauchy sequence. So this is where you have to be careful with respect to d1. Yeah, because we want to show d1 is complete, right? So we have to assume we have a Cauchy sequence with respect to D1, and we want to show it, converges basically. So the first step, so step 1, xn is Cauchy in d of xy. So that follows from, let me just call this 2. So this will follow from 2. Why? Because let's sort of show it, right? So in order to show it's Cauchy, I need to show, for all epsilon bigger than 0, there exists n such that for nm bigger than or equal to n, d of xm ym is less than epsilon, right? But so let's let epsilon be bigger than 0. We're going to use 2. So we have that, from here, let me just write star. Star is Cauchy in D1, right? So for all epsilon 1, there exists n1 such that for nm bigger than or equal to n, d1 of xm ym is less than epsilon, right? So that's by assumption, because we're given xn is Cauchy with respect to d1. So what I'm going to do, there should be epsilon 1. So epsilon 1, right? So what I'm going to do is, since for all epsilon 1 bigger than 0, let epsilon 1 be root, let me think real quick, 1 over k epsilon. Yeah. So there exists n1 such that for nm bigger than or equal to n1, d1 of xm ym is less than 1 over root k epsilon, right? So I'm going to choose my n to be n1. Then for nm bigger than or equal to n, I have distance of xm y. Whoa, what am I doing? Why do I have y? Sorry. It should be, I don't know where my y came from. xm xn. Yeah, sorry, I don't know why. Yeah, xn. Yeah, it should be like xm minus xn, right? So do I have? Okay, good. Xm xn is smaller than or equal to, so I'm going to use 2 root k times the d1 of xm xn, and from here, from this part, I get that it's smaller than root k times 1 over root k epsilon, which is epsilon. Yeah. So you can see that, from here, xn is Cauchy, and xn is Cauchy with respect to d. Yeah. Is everyone clear so far? The fast way is just to say, if d1 is smaller than epsilon, then d is smaller than epsilon, because d is sort of, less than d1. That's sort of the idea. Yeah, up to some constant. So is everyone clear so far? Sorry for the y. I don't know why I put y. Okay, now we could use lemma 13.3. Exactly the proof I wrote, right? 13.3, second sentence, to say xn Cauchy in R for all I, right? With respect to D. And then R is complete. So xni converges for all I. And then, it's the wrong proof I wrote, but the wrong proof is right for D, right? So lemma 13.3 first sentence says I converge in, R if and only if the whole thing converges, right? xn converges in RK. So again, everything here is with respect to D. So converge RK with respect to D. So distance xn. So I'm gonna just write converges to x. Yeah. So without loss of generality, we just let x be the limit. Yeah. So so distance xn to x goes to 0 as n goes to infinity. Okay, but our goal is to show d1 of xn as x goes to 0, right? Because we want to show the sequence in d1 converges, right? And that's when we use 1. So fast way is, d1 xnx less than d xnx. This thing goes to 0, right? So since this thing's smaller, it has to go to 0, right? Because distance is always positive. So that's the fast way, right? But we had to do the epsilon proof, right? So it's not hard. So let epsilon be bigger than 0 as dxnx goes to 0. There exists n such that for n bigger than n, d of x and x less than epsilon, then you get this, right? Then for, and then you're done. This thing converges, right? So you see here, I'm using 1, right? So you see you need 2 ways, right? The first, this 2 is to show that it's Cauchy in D, and then 1 is to show it converges in D1. So is everyone clear so far? So D1 is complete metric. Let me just write that. Metric. Is everyone clear? Hopefully. Wow, that took a long time. Is it okay if I just do the bounds? It's the same exact argument for. So now that you know D1 is complete, so now lemma 13.3 holds for D1. Yeah. And you do the same thing for D2. So D1 is, how is D1? D1 of xy is this, right? So again, without loss of generality, let's assume it's, x1 minus y1 without loss of generality. Let's assume the max is like the first term. Then d2 of xy is this, right? So since I'm summing, I certainly have this, right? I mean, d2 contains x1 minus y1, right? So, but d2 is certainly smaller than what? So this thing is smaller than if I just sum over the biggest one, right? If I just sum over x1, y1, k times, right? Because x1 minus y1 was the biggest one. So if I replace all the smaller ones with the bigger one, I got something bigger. And this is k x1 minus y1, which is k d1 of xy, right? And then, again, now that you know D1 is complete, D1 is complete, so same argument, right? So is it okay if I stop here? It's the same argument, everyone good? Pretty much the same argument. I guess, to show it's, I guess here, instead of, multiplying by k, so I guess here, I guess here you use that Cauchy in D2 is kind of the opposite, is Cauchy in D1 by the first one, right? Because it's smaller. So by, I'll call this 3. This time it's swapped. It's Cauchy by 3. And then convergence is in D1 leads to convergence in D2 by 4, right? Because D1's bigger. If D1 converges, then D2 converges, right? I mean, you might have to like divide by K, but leads to convergence in D2 by. But does everyone get the idea, at least? I guess that's the most important thing. Is everyone clear? Good. Okay. That took a long time. I did not expect that. Okay. Let's move on to more questions from from chapter 13. So yeah, I realize that this chapter might be hard for people because it's very not numerical. It's very proof based. So let me talk about 13.7 really quick. Yeah. So remember 13.7. If I have an open set U, right? This is pretty important fact to know. I mean, for the future, it's open. So I could take for all x, there exists a ball of radius that depends on x contained in U, right? That's what it means to be open, right? To be in the interior, there's a ball that lies in your set. So U is certainly contained in the union of x and U. Since every ball contains x and a union over all x and U is certainly contained in the ball. But the ball is contained in U. Every ball is contained in U, so this is contained in U. So you see that U is actually a union of balls. So this is what we had last time, right? And balls are intervals, right? So technically, we proved everything here. We proved up to here. We just need disjoint, right? So the problem is making them disjoint. So there are many ways to argue this. So instead of working with balls, I'm just going to take the largest interval. So, let Ix be the largest interval containing X. Okay, why does this exist? Well, we have one interval, right? So why does this exist? Well, we have one interval. We have BRXX, right? So one interval certainly exists. So why does a large one exist? Well, let Ix be the union of all intervals containing X. So, I mean, this is one particular proof. You don't have to do mine, but now a priori, union of intervals need not be interval, right? Example 1, 2, union 3, 4, not interval, right? But if they share a common point, it's going to be an interval, right? Like 1, 2, union 1/2, 5 is 1, 5. Sorry, all open intervals. Yeah. So and the union is open, right? Because you learned that arbitrary union of open sets is open. But since they all contain X, the union will be an interval. So certainly this is true, yeah? Now, what we're gonna do is we're gonna show two things. So we define X is equivalent to Y if and only if Ix is Iy. Now, here's a nice thing, yeah? We have for all xy in our set, xy in U, either Ix intersect Iy is empty set, which means they don't intersect, or Ix is Iy. We can't have, anything else. So the reason for this is if we are in case one, done. If not, assume the intersection is not trivial. So contains at least a point, right? At least one point. But then the union will be an interval, right? by the argument above. So by here, right? If two intervals contain a point, the union will be an interval. But this will be an interval. This is an interval that contains x and y, right? In particular, it contains x. But Ix was the largest interval containing x. So it has to be that, Ix is Iy, right? You can't have anything bigger, and or else it's a contradiction. So you can write U, and so you write U as you identify all the ones that are equal. So if the set of X in U without equivalence, and then of like Ix. Yeah, so this will be disjoint, right? Because we sort of identify all the ones that are the same, right, that are equal, and then we put them all in the same class, and then the rest have empty intersection, so they're disjoint. So this is one way to do it. Yeah, okay. Not very important, but I honestly, the most important thing is this. U is union of balls, yeah? And then just know there's a proof that, that makes them disjoint. Whoa. Okay, any questions so far? But pretty cool, right? The open sets look very nice in R. Okay, so I'm gonna do some compact stuff, right? So let's do 13.12. SD metric space. Show E is closed. If E is a closed subset of a compact set, then E is compact. So, so 13.12. SD metric space. A, if E is closed subset of compact set F, E is compact. So again, it never said S was a subset of R, right? So you can't use the compact if and only if closed and bounded. So you have to use this open cover argument. And I think it's pretty nice because I feel many people are not familiar, are not comfortable with open covers, right? So again, to show E is compact, I need to show every open cover has a finite subcover, right? So let's do this. So let's let U alpha, the set of U alpha be an open cover of E. So i.e., E is contained in union alpha. Sorry, my U's might look like the union. U, right? Where U alpha is open, right? Now, what can anyone tell me about F without E? If I take the set F without E, is that open, closed, neither, both? What is it? Anyone? So E is a closed subset, right, of F. So what do you know about the complement of a closed subset? One. Yeah, it's open. So and now, what can you tell me about this? Union alpha U alpha, union F without E. This one covers E, and this thing is the set of points that are in F without E, right? So F is contained here. Agree? And this is open. This is open, right? Because arbitrary union of open sets is open, and this is a union of open. So this whole thing is open. So this is an open cover of F. Yeah. And what do we know about F? It's compact, right? So there's a finite one, right? So as F compact, you know, F is contained in, it could be just, it's finite, right? So let me just, I equals 1 to K UI. No, this one. So it could be just the UIs cover F already, but let's just union F without E. It's just an extra one, right? It's still finite. So, right, it could have been UI covered the whole space anyway, but so this is a finite thing. Well, here, then you could check that E is covered by this then, right? Because this has no effect on E. So you could check that E is now covered by this, and then you're done, right? Because, this thing covers F, this thing doesn't cover E, so it must be this thing covers E. And you have a finite subcover. Okay, is everyone clear on that? Good, great. So let's do more. So I'm gonna just keep moving on. So let's do like, I don't know, 13.3, yeah? So E is compact, non-empty subset of R. Show sup E is inf E, belongs to E. So, E compact, non-empty subset of R. Show sup E, inf E, belongs to E. Okay, now since here's a nice thing, it says of R, so you should always notice this, maybe for your final. If it says compact, just pray it says of R, because if it's compact, we know an alternate definition, right? It's closed and bounded, right? So as E is compact subset of R, E is bounded. So in particular, sup E is not infinity, right? It's some number alpha, and inf E is some number, let's say beta, yeah? So we get that because E is bounded. Okay, so can anyone tell me something about the sup? Do you agree that then there exists, I don't know, En in E such that En goes to alpha, and I don't know, En prime in E. Does everyone agree with this? So again, one way to do this is, if here's the sup, you do alpha minus a half. There has to be a E1 here. There has to be a point in E in this interval, right? From alpha minus a half to alpha. Because if there's not, alpha minus a half is my new upper bound. And that contradicts the sup, right? Sup is the smallest upper bound. So you see there has to be a point here. And then, I mean, you can construct it, right? Alpha minus a fourth, and then there's an E2 here. And then that'll be your En, right? You keep going. So is everyone clear with that? That's the nice thing about the sup, is that you can relate it to limits. It's like a limit of there's a sequence going to it. Great. Now, again, we haven't used the other part, right, where E is compact. So E is bounded, but also E is closed. So if E is closed, and I have a sequence in E going to alpha, what do you know about alpha? What does it mean to be closed? Anyone? So what does being closed mean? So how about this? Let's go back. So, right here. The set E is closed if and only if it contains the limit, right? We can always relate closeness with like limits of sequences, right? So it's closed if and only if it contains the limit of every convergent sequence in E. So does everyone see why we are convergent sequence in E means the terms are in E. It means like if you have a sequence in E that converges to something, you contain that. So the closeness just means you contain all your limit points pretty much. So here basically, let me just write E is closed if and only if, for all, I'll call the sequence Sn in E going to S is in E. Yeah, that's what it means. Like you contain all your limits pretty much. So here, En is a sequence going to alpha, so you contain alpha. So alpha is in E. Similarly, beta is in E. Is everyone clear on that? I mean, that's pretty much what it means to be a limit, right? So again, like for example, like this set is not closed because you don't contain, there's a sequence going to 1 and a sequence going to 2, but you don't contain 1 and 2, right? So since you don't contain 1 and 2, you can't be closed because you don't contain the limits, right? So not closed. Yeah. Is everyone clear so far? Hopefully things are making sense. Metric spaces are making sense. So, okay, great. So let me I sort of did the the interior and boundary. So I did the closure, but someone asked me in office hours, so I guess it's a good problem. So let's find closure and interior. It's similar to the previous things we did of irrationals. Yeah, so R without Q. So let's call this E. Yeah. What is the closure of E? So let's practice this. So closure, you need to contain all your limits, right? In particular, you contain E, right? Because you just define, for anything in E, just define the constant sequence, E, 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 E. So that thing converges to E, so it has to be in the closure. So certainly E, the closure contains E, but does it contain anything else? What do you all think? So my set is the irrational numbers. What is the closure? So the question is, I have the irrationals because I contain E. What's left? The rationals, right? So the question is, can you find a sequence of irrationals going to irrational? Is that true? Anyone? How about, it's this argument. So here's a rational. Let's take Q minus a half, Q plus a half. Does everyone agree there's an irrational in this interval? Yeah. So given any interval, you have like infinitely many rationals, infinitely many irrationals, right? So just pick R1 to be my first irrational. Now I take Q minus a fourth, Q plus a fourth. again, there's a R2, right? So you could find a sequence of irrationals Rn going to Q, right? So this is an R without Q. But to be closed, right, you need to contain all your limits. So in other words, you have to contain all the rational numbers. So what is the closure? Can anyone tell me? Anyone? So I must contain all my limits, right? So I must contain the rationals because I've just found a sequence going to it. And I must contain irrationals because that's my original set. So I must contain rationals and irrationals. So the closure must be all of R. Yeah? Now what is interior? Again, what does it mean to be interior? So X in E is in E interior. If and only if what? There exists R bigger than 0 such that my ball lies in E, right? That's what it means to be in the interior. Is everyone clear so far? Great. Now, if I pick X, let's take any ball, right? X minus, this is my ball. Can this interval, can this be contained in E? Is the question. So remember, E was the irrationals, right? So this ball must be contained in the irrationals. Is that possible? No, I mean, no matter what R is. I mean, R bigger than 0, right? But no one's talking. So given an interval, do you agree by density of rationals, there's a rational inside? There is rational inside. I mean, if this is the case, if there's a rational inside every ball, I can't be contained in the irrationals, right? That's just not possible. Your ball contains rational numbers. You can't be contained in E, right? So E interior is the empty set. Yeah. No matter what ball you choose, I mean, pick any point in E, draw a ball around it. You're not going to be contained in E, right? Because you contain rational numbers. So this is the empty. So you sort of see here. Let me just pick a note for people. Open, closed is not like complete opposite, right? So what I mean by this is if E is closed, what does that mean? E is E closure, right? I mean, the closure of a closed set should be closed. And if E is open, then E is equal to E interior, right? Every point is an interior point. But you see here, E is not equal to E, closure, and E is not equal to E open. And I mean, an easier problem is E is 1, 2. So E is not open, right? Because ball around 2 leaves the set, right? Because you'll have values bigger than 2. But E is not closed because you don't contain 1, right? Because you don't contain 1. Yeah, so taking complements, complement of open is closed, but taking complements is not exactly opposite, right? So, a set need not be open, need not be, need not be closed. It could be neither, and it could be both, right? So example, so this is neither, right? And then R is open and closed. Why? Because it's the whole space. So, but yeah, so just keep that in mind. Yeah, a lot of people make that mistake. So, okay, any questions so far? Okay, great. So, I mean, I have time for one more. So let me just go back and do 13.12 part B. Show that finite union of compact sets and S is compact. So again, because I figure people, need help on open cover stuff. So, great. So let's let S the metric space. And what was the question? So show finite union of compact sets and S is compact. So show of compact sets in S is compact. So you see, if they said this was in R, S was a subset of R, this is easy, right? Because what does it mean to be compact? Closed and bounded. So you just need to show a finite union of bounded sets is bounded and finite union of closed sets is closed. Finite union of closed sets is closed was like a theorem or something. It was like De Morgan law. So technically you just need to show finite union of bounded sets is bounded. So you see it's pretty easy, right? So that's why they didn't really specify S was a subset of R. Or else it would be a too easy of a question. So let's let let E be a union of finite, okay, EI, where EI compact for all I, right? So I need to show E is, compact. So what's the first step? Again, it's take any, no one? Take any open cover of E and show it has a finite cover, subcover, right? So let's let E be contained in, I'm going to skip the wording, yeah, because we're running out of time. U alpha, where U alpha open, right? So this is an arbitrary open cover of E. So we need to show it has a finite subcover, right? But E is this. It's the union of this. So union alpha U alpha covers EI for all I, right? Since EI's make up E and it covers E, it certainly covers each EI. So so let's say, for E1, as E1 is compact, there's a finite subcover, right? There exists, I don't know. I'm really bad with notation. So there exists finite subcover E1 contained in U1J, yeah. And I'm just gonna, I'm just gonna say union J, yeah. I mean, and then where this is finite. And similarly, E2 contained in union J. So it could be different numbers, right? So, I don't want to specify, but this is also finite. It could be like E2 requires 6 sets, 6 open sets, E1 requires 5, but it's finite, yeah? And all the way to, how many did I have? I have EK. So EK contained in union J, UKJ. Yeah, so what is your finite subcover? Well, each one covers each component. So you have union J, U1J, union J, U2J, union J, UKJ. Yes, this is what I mean by I'm really bad with notation. this covers E, right? And it's finite because it's K unions of union of finite sets, right? Of finite unions of open sets. Yeah, I mean, this is finite. All these are finite, and I have K unions, which is finite. So this thing is a finite subcover. Yeah. So hopefully that this clarifies metric spaces. Yeah.